Well, it's 9:01. I think we will get started. Hi, everybody. Welcome. Um, this is Karen Hauk from UC Berkeley. It's Solar Week this week. Today's the last day, and that is where solar scientists answer your questions about the sun and life as a scientist. And today we're really excited to have Dr. Holly Gilbert, who is the director of the Heliophysics Science Division at Goddard Space Flight Center. This webinar will last for about 30 minutes, and you are encouraged to ask questions along the way rather than saving them for the end. The webinar today is called Touching the Sun, A New Age of Solar Science, and welcome, Holly Gilbert.
Thank you. Great. Well, I'm really excited to be here, and thanks for inviting me to talk about the sun, my favorite topic. Even though I'm the director of the Heliophysics Science Division, which involves not just the sun, but also physics throughout the heliosphere, my background is in solar physics. So that's why the sun is probably my favorite topic. And it's really particularly exciting right now for NASA because we have a couple of new missions that I'm going to talk about. And before I go into those missions, though, I want to kind of explain why we are sending these missions, which are going extremely close to the sun. Why are we even doing that? It definitely costs a lot of money. It's exciting, but let me tell you about some of the mysteries, the scientific mysteries that we're hoping to help solve with these two new missions. So first, let's just start by looking at the sun. The sun is this beautiful ball of fire in the sky, and it seems relatively quiet unless you know more about the sun and the science behind solar physics. In fact, it's a very dynamic star, and some of you, or most of you, are probably familiar with sunspots, which are these dark splotches on the sun. And the surface of the sun, called the photosphere, is it's a uniform-ish temperature, about 6,000 degrees Celsius. As I was saying, the photosphere is the surface of the sun, but there's a complicated atmosphere above the surface, the visible surface. Of course, the sun is a ball of hot plasma, so it's not solid, but there is this surface called the photosphere. And one of the biggest mysteries of solar physics is why the temperature of the different layers of the atmosphere is so different. And you're seeing this sort of movie going through the different layers and therefore the different temperatures. And as you get away from the surface of the sun, things get really, really hot. So where we started at about 6,000 degrees, now we're going above 1 million and above 3 million. So this very, very hot outer atmosphere of the sun called the corona. We don't fully understand why this is. If you have energy that's being generated at the core of the sun, as you move away, it's like a campfire, things should get cooler. And they do for a while, but then all of a sudden, when you hit the atmosphere, they get really, really hot in a very, very short distance. So this is kind of crazy, and we don't fully understand what's going on and how that energy is being transported. And so here's a nice composite image of the sun in different temperatures and 3 different wavelengths that show those temperatures. And this is very hot. I think these temperatures are between 1 million and maybe 3 million. So you can kind of see the structure. It's very complicated. These are magnetic field lines that have hot plasma on them, and you can see the loops. And that's really the important thing, is that the sun is magnetically driven. All these magnetic fields have everything to do with all the activity on the sun, and the sun is very active. And in fact, my background is studying solar eruptions, and so this is a really interesting area for me. Okay, so mystery number 1, why does the temperature rise as you move away from the surface, and so significantly? I mean, above 1 million degrees, that's really, really hot, of course. I mean, the surface is hot as well. But again, it involves the transfer of energy, and I mentioned the magnetic fields, but it's really that transfer of magnetic energy into the plasma, or those charged particles. Plasma is just a very, very, very hot gas. It's so hot that the atoms can't hold on to their electrons. And so you've got these electrons and ions floating around. And that, when they're floating around, that generates magnetic fields. So these are very, very tightly coupled or associated. Now, this is a movie of some of the solar eruptions I briefly mentioned. Now, all that magnetic field energy and how those magnetic fields are interacting can cause these really big solar eruptions that you probably have heard about, the coronal mass ejections and solar flares. And so this is one of the reasons we are extremely interested in this. It's very interesting but from a scientific point of view, but this kind of activity can impact us here at Earth. And this is what we call space weather. So when these storms, when these huge bubbles are directed at the Earth, they interact with the Earth's magnetic field, and they can cause kinds of problems with our technology, our satellites, our power grids. So it's an important field that we study, the space weather, and we have a long ways to go before we're able to actually predict, and we do some forecasting for our satellites. Luckily, we're protected here on the ground from the Earth's magnetic field and the atmosphere, so that protects us from these particles, these energetic particles. But again, it can cause currents, and that causes problems with some of our technology and our satellites. One other interesting thing is it's not just those bubbles that are blowing away from the sun periodically. There's a constant solar wind. And this is Ulysses is a great mission from a long time ago that discovered that there's this outward expansion of that solar atmosphere, and we call it the solar wind. And there are different speeds, so it's not constant. There's very, very fast solar wind. You can see here at the top and the bottom. And then there's slow solar wind. And I mean, it's not a huge difference, but they do go at different speeds and they have different compositions. So it's kind of a complicated atmosphere, really. Okay, but one of the other mysteries is how does the solar wind, how is it continually accelerated and blowing away from the sun? Now, again, we're looking at the coronal mass ejections. The solar wind you can't really see it because it's very, it's not nearly as massive, but it's constantly there. It's very diffuse. Okay, so this is another mystery that we've been trying to solve. And again, this is just to kind of review the eruption part of this. If the corona is unstable because of the interactions of the magnetic fields and that magnetic energy being transferred into different temperatures, and also the plasma and kinetic energy. So there's a lot of different types of energy that lead to these eruptions, and they're huge. There's billions of tons of material, and they are fast. Some of them are extremely, extremely fast. So if you imagine traveling from Washington, D.C. to LA in a matter of seconds, that's how fast they are traveling. Okay. Mystery number 3, along with these coronal mass ejections and all of this activity, this is kind of a complicated graph, so you don't really need to understand it, but the point is that there are these places where particles are really energized. So not only is that coronal mass ejection carrying a bunch of these charged particles and magnetic field, but there are these processes that we don't fully understand how and where they're happening that cause particles to get extremely energetic. And again, that leads to some of the effects of space weather. And so we really would like to better understand where this is happening, why it's happening, and what's causing it. And this is a little dramatic, our violent sun, but again, this is showing some of the effects of space weather. Now, you can see the power grid going out in a big part of North America due to a solar storm in 1989. And the other thing that you're seeing is the aurora, which are actually a beautiful consequence of space weather. So if you've seen the northern lights, that's really, you're watching the sun's particles interact with the Earth and the Earth's magnetic field and the atmosphere. And so that in itself isn't dangerous. It's beautiful if you can see it, but those processes lead to currents and other things. So we need to go close to the sun to figure out some of these mysteries. And that is because close up is where that action is happening. So these storms that are getting erupted away from the sun are really starting closer to the surface. I mean, we're far away. We're 93 million miles away. So we really want to sample the region where this stuff is happening, where this very explosive processes. So we've had this concept in mind for a long time about sending a probe very close to the sun. And so Parker Solar Probe is a mission that NASA launched last year, and it is going very close to the sun. Now let me explain how close that is. Now it may seem like not that close. It's about 3.9 million miles away from the sun, But think about that. We're 93 million miles away. So if you look at a football field, so we're getting within 5% of the distance that we are from the sun. That means that we're sitting on like the there we go, the yard line, right? So we're really, really close. Mercury would be at the sun's 35-yard line. Venus would be at the Earth's 28-yard line. So you're getting closer to touchdown. And even the coronal loops, those magnetic fields that are showing the plasma in these beautiful loops, those extend pretty far out as well. Helios is an older mission and it got fairly close, but really the closest that we are currently going is within that 4 million miles. And we've already made some close approaches, not the closest approach yet. So there's kind of a visual of how close that actually is. Also, Parker Solar Probe, when it's going in that interesting orbit close to the sun, it's going really, really, really fast because it's getting close to the sun, which is very, very heavy and it has a lot of gravity effects. So Parker, when it does closest approach, will be going over 400,000 miles an hour. So it's very, very fast, the fastest man-made object ever. Okay, so why did it take us so long to send a probe near the sun? Okay, a lot of you probably have never seen a rotary phone, but it's kind of a similar thing in terms of the technology leap. We had to wait for technology to advance enough where we could send something that close to the sun, because as you probably can guess, you get close that close to the sun, it's extremely hot, and you have instruments that you're trying to protect. Now, Parker has this wonderful thermal protection system, and it involves a big heat shield, about 4 inches thick, and also a way to get the heat away from all the instruments. So it's really, really neat. Again, if at the closest approach, within that 4 million miles, the heat shield will be at about 2,500 degrees Fahrenheit. That's really hot. But everything behind that heat shield, all the instruments are going to be at like room temperature. So it's a very effective way of protecting the instruments from this massive amount of heat. But again, this isn't until fairly recently that we were able to do this. Now, the other mission that I wanted to mention is associated also with trying to solve these mysteries, and it's called Solar Orbiter. And Solar Orbiter is actually led by ESA, which is the European Space Agency, but we are a partnership with them on this mission, and so NASA is also involved, and this one has not launched yet. So Parker Solar Probe launched last year, over a year ago. Solar Orbiter is going to launch in February. So keep your eyes and ears out for that. That's going to be an exciting event. And Solar Orbiter is going close to the sun, not as close as Parker Solar Probe. It's going within Mercury's orbit. And the unique thing about Solar Orbiter is it has 10 instruments. So Parker Solar Probe has 4 instruments, and it's basically sampling that corona and figuring out what the fields and that plasma are doing. But Solar Orbiter has in situ instruments like Parker Solar Probe, but also remote sensing. So it's able to take pictures and images of the sun along with the sampling. And so these 2 missions together are going to be fantastic. And this is just a demonstration of the orbit of Solar Orbiter, because this is what's really unique also, is that its orbit will get kicked out of the ecliptic, and it's going to use Venus. It's going to fly by Venus a few times to get it out of the ecliptic, because that's a very hard thing to do. It takes a lot of energy. So Parker is in the orbit of the plane of the sky, or of our solar system, or of our planets, but Solar Orbiter is going to kick out of the ecliptic. Okay, so why is that important? Well, we really have not ever been able to image the poles of the sun. And that may not seem that important, except for when you look at the magnetic field of the sun, it's extremely complicated, but the north and the south, the main poles, are where a lot of that magnetic field originates from. And we need to model the poles in order to understand how all those other magnetic fields around the sun are working. Now, here's an example of what we might discover when we image the poles of the sun. So if you take a look at these 2 things, I challenge you to identify them, because this is an example of looking at something from a different point of view and really seeing a totally different image. So that's Jupiter. Now we're used to seeing Jupiter from the side, the big red spot, but this is Jupiter's poles. And so look how different that is. We can really see a lot of neat detail. And that's Saturn from the poles. So again, when we're able to see the entire sun, we're really hoping to make some discoveries about what's happening at the poles and how that relates to what's happening everywhere else in the sun. And that will help us lead to better prediction for space weather, and that's how it impacts us here at the Earth. Now, NASA is also interested in space weather because we have missions, not just near the Earth that are orbiting near the Earth, but in other places in the solar system. So we also want to be able to forecast when these solar storms might be going towards one of our missions. Like we have missions at Mars, at Mercury, and so NASA has an additional interest in space weather because of that. Now, we are also going to be sending humans back to the moon and to Mars. And I don't know if you remember when I said on the surface of the Earth, we're protected from these very charged energetic particles that are coming from these solar storms because the magnetic field of the Earth and the atmosphere protect us. It basically deflects this stuff. And so the astronauts that are going above and higher above that magnetic field or that magnetic shield are going to be more exposed to some of this radiation and these very energetic particles. And so we also want to be able to predict and to forecast space weather to better protect our astronauts, and especially on a long, long trip to Mars. And it's not that they would die instantly if they get hit by one of these, but it's really an additional amount of radiation that they don't necessarily want to be exposed to. And so that's a kind of a crash course on some of these things related to solar physics. I'm sure throughout the week that hopefully some of these questions and facts have been answered, but that was kind of what I wanted to hit on. It was just those two new missions. One has already launched, Parker Solar Probe, and one's going to launch in a few months, and that's very exciting. And they will work together to produce, hopefully, some groundbreaking science. And I think that was it. So I'll open up for questions. Does anybody have any? Or that was kind of a lot of information in a short amount of time.
Hi, Holly. There were a couple of questions that we got. One was, are solar storms dangerous? Which you have definitely touched on, but maybe you have more to say.
Yes, so they're dangerous to our technology and to astronauts that are above that magnetic shield. But again, luckily, we're protected here on the surface. But they're dangerous for GPS, for our satellites that are orbiting the Earth. And if we lose GPS, it's not just inconvenient for those of us that depend on it, but that also can be dangerous for airlines that depend on very accurate GPS to land, ships that are navigating. And so in that respect, that creates a bit of a danger. And also our power grids, because of these currents from these charged particles that are going on in the polar region, they can cause currents in the ground, which can cause power outages, which could potentially be dangerous if they last for a very, very long time. So like on the East Coast here, we have we have a lot of people. We have a lot of cities that are close by, and if all the power went out in those cities for 2 days, you can imagine people would panic, and that might end up being dangerous in that respect, in an indirect way. But they're not dangerous in the fact that if we get hit at the Earth by one, we're not going to feel the effects directly on our bodies, but our technology will.
Okay, thanks. There are two questions that I think are related. One of the participants here has asked, will the sun ever explode? And we also had a question, how soon will the sun go supernova?
Okay, great questions. Luckily, we don't have to worry about that because it's going to be a long, long time before the sun dies out. It has a lot of fuel to burn through. And so on the order of 4.5 billion years left. So the sun is about middle age. And so we have a lot of time to be concerned about that. But what will happen is it will burn through all of its fuel eventually, and it will collapse on itself, and then it will be in a huge expanded red giant. So there's these processes that go on when the balance of the gravity and the expansion and all of those forces go unstable, and that's what causes a red giant. So it won't be supernova. It's not a massive enough star. So it will actually end up being just kind of a quiet white dwarf. Now, for stars that are a lot more massive than the sun, they can eventually die and turn into a black hole, but it requires a lot of mass for that to happen. So the end stages of stars is a very interesting area that people study, and it's exciting. And luckily, we can think about it without being worried because we won't be here.
Sorry, I was muted. So what new and exciting facts has Solar Probe revealed as it gets closer, and is it as close as it's going to get?
Great question. So it's been near the sun, but not as close as it's going to approach. So it takes a few years, a few orbits to get to that very, very closest approach. So it's, I think, about 7 years. So, but we have gone through our first sort of close approach. And to be honest, the scientists have been writing papers, the scientists involved with the mission, and that data hasn't been publicly released. In a couple of weeks it will be. And then at a scientific conference, they're gonna tell us about all the new exciting stuff that they have discovered. It's not public yet, so I can't really tell you exactly what, but I suspect, based on knowing that there's a lot of papers coming out, I think that there's gonna be some information about the regions where these magnetic field lines are interacting and where the particles are getting really accelerated. And so with Parker being able to go closer to the sun, is going to be able to sample some of those regions, and they're all going to be a little bit different. When those storms and when the wind, by the time it gets all the way to the Earth, it's kind of it's all similar. But Parker is sampling those solar energetic particles kind of where they originate in their pristine state. And so that's very useful information when we're really trying to understand some of the fundamental physics behind the magnetic field interactions and how that reacts and interacts with the plasma as well. So stay tuned. In a few months, we're gonna hear about the really exciting, groundbreaking science. And I know that there is some, but they're kind of holding it close until they have the release of the actual papers and the research papers, so.
Why do some stars die more quickly than others?
Oh yeah, good question again. So stars, there are different classes of stars, and so it really depends on how massive the star is and how active, meaning how fast is it rotating, what are the magnetic fields like, and how big are the magnetic fields, and how massive is the star. And those all factor into how quickly and how the end of the life of the star looks like. So some of the more active, very, very big stars don't live as long. I mean, they're so active. I mean, this is a very simplified way of describing it, but they're very, very active, and they burn quickly, and then they die more quickly than some of the other ones that are smaller. So it really is just dependent on the size and the activity and the properties of the star. And so there's a wide range of different types of stars.
So switching to black holes, at this time, do we know what's inside a black hole?
No, black holes are not probably, I think they are absolutely the most strangest, mysterious things in the whole universe, really. We don't exactly fully understand if anything is in black holes. I mean, even space-time, how is this surviving such a very, 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 very massive point or area? So black holes are so massive, the gravitational pull is so extreme that really nothing can survive even close to it. But what we can see, I mean, they're black because we can't really see inside them, or we don't really even know if there is an inside. But what we can see is that effects of those very strong gravitational force, making all the stars that do get within close range, they're spinning, and it gets them way spun up and energizes them. And so we can see the light coming from those very energized stars and material that's getting too close to the black hole, but we don't fully understand the physics that are exactly right in the black hole. So it's a very interesting area if people are interested in trying to study something that is extremely curious and surprising.
Well, let's see. It looks like we have a few more minutes. What advice would you give to girls who are interested in space science?
I highly recommend going and taking a lot of physics courses and asking tons of questions. And it's really, really fun. And do not be afraid to explore and to try different things. I thought originally that I was going to become an astrophysicist, which is, solar physics is kind of part of astrophysics. But it wasn't until I did an internship when early on in college at a place that looked at solar images and studied the sun. And I couldn't believe how complicated it was and how neat it was. And all the images were just beautiful. And had I not ever started that internship there, I would not actually have known that for quite a while into my education. And the sun is it's in our backyard in terms of astrophysics. So it's kind of a neat thing to study. We can learn more about the sun than we can objects that are far away. So I just take risks and don't be afraid to ask questions and be curious.
Great, thank you so much. That might be a good note to end on.
Okay.
Let's see, we have, thank you everyone who participated today. Please click on the link that's in the chat room to answer a quick survey about the webinar. That really helps us. And go on Solar Week and ask a question. We also have an answer garden. The link is also in the chat, and that's just a place where you can type a quick question about the sun and then look on Solar Week and get the answer for it. And thank you so much, Holly Gilbert.
Yeah.
It's been great hearing from you, and thanks for taking the time to be with us today.
Yeah. Yep, my pleasure. Thanks for having me.